Welcome to the submodule 1 of 4 Terminology and Directional Calculations. Before we dive into the technical content of this module, let's take a moment to review what you'll be able to do by the end of the session. These objectives outline the core skills and knowledge you'll gain, each of which plays a crucial role in modern directional drilling operations. First, I will explain why surveys are required in wells, why we even bother with surveys in the first place. Then, I will define major terms used in survey calculations and cover terms such as measured depth, true vertical depth, inclination, azimuth, dogleg severity, displacement, and more. These terms form the language of directional drilling. Whether you're on the rig floor, in the office, or interpreting MWD data, fluency in this terminology is essential for effective communication and operational decision-making. Third, I will describe the difference between the two most commonly used survey methods, which are the minimum curvature method and average angle method, which are the two most commonly used techniques to calculate a well's path between survey points. Then we look at conversions, first between rectangular and polar coordinates, and secondly from quadrant to azimuth. Then we will explain what dogleg severity is and its components. Finally, I will demonstrate how to plot directional surveys onto a conventional plot. So let's begin. Surveying is one of the most critical elements in drilling operations because it directly impacts technical, safety, and regulatory outcomes. First, accurate surveying ensures we meet our reservoir and drilling objectives by steering the wellbore precisely to the geological target. This includes hitting the reservoir at the right strike angle, which is often vital for maximizing reservoir contact and ensuring long-term production performance. At the same time, surveying allows us to avoid problematic zones such as salts, faulted formations, or areas of abnormal pressure that could compromise well integrity or lead to costly non-productive time. Secondly, to maximize production by avoiding problematic zones such as salt domes. A third key role of surveying is anti-collision. As drilling density increases worldwide, the risk of wellbores intersecting with nearby wells or encountering lost objects is rising. Reliable survey data ensures our trajectory remains clear of these hazards, protecting both the drilling program and existing infrastructure. Finally, surveying underpins compliance with legal and regulatory requirements. Accurate well positioning ensures we do not cross lease lines, property boundaries, or borders, which could have serious financial or legal consequences. Meeting government and industry standards through precise surveying helps operators maintain a license to operate while demonstrating commitment to safe, responsible, and efficient drilling practices. In wellbore surveying, several key terms are used to calculate and describe the position of the borehole. The well reference point O is tied to structural or field references, but applies only in the horizontal plane. The surface location S is a three-dimensional reference point from which measurements begin. A survey records inclination, azimuth, and depth from the Kelly bushing RKB at each station in the borehole. The vertical section plane, also called the plane of proposal, is a vertical plane passing through the surface location and the target. Azimuth, AZ, defines the direction in degrees clockwise from north, while inclination, INC, is the angle in degrees from vertical. Measured depth, MD, is the distance along the well path, and true vertical depth, TVD, is the vertical distance from the surface to the well reference point. Horizontal displacement, HD, is the straight line distance on the horizontal plane, while vertical section, VS, projects the borehole onto the plane of proposal. Dogleg severity, DLS, describes the rate of directional change over 100 feet or 30 meters. Finally, references such as KB, RKB, RT, and RF define the rig datum relative to mean sea level. Okay, so quick question. What is the purpose of the vertical section plane in well planning? I will stop for a moment for you to think about it. When we are looking at a well plan in 2D, we break the plot into a plan view and a vertical section view. When looking at the well from the side, you can see that viewing it from certain angles can show far more detail than others. Usually, looking at the well from a plane which is perpendicular to the direction from the start to the finish is the best angle. This is the vertical section plane. Let's continue to walk through essential directional drilling terminologies that are critical for understanding wellbore trajectory control and subsurface navigation. First, we have the build angle, used here as a verb. This refers to the act of increasing the inclination of the drilled hole. In vertical drilling, the hole goes straight down. However, in directional drilling, we intentionally deviate from vertical to reach a target that is offset from the surface location, like a reservoir that lies beneath a restricted surface area. The process of changing the angle of the wellbore from vertical to a desired inclination is known as building angle. This process involves specific downhole tools such as steerable motors or rotary steerable systems, RSS, along with real-time measurements of inclination and azimuth to guide the trajectory. Next is the build-up rate, commonly abbreviated as BUR. This is the rate of change of the inclination per 100 feet of drilled hole, typically expressed in degrees per 100 feet. A higher build-up rate means the wellbore is turning more sharply. This value is crucial when designing well paths, particularly in build sections, where the well transitions from vertical to a higher inclination. Engineers must ensure that the BUR is within safe mechanical limits to avoid excess stress on the drill string and to prevent issues like doglegs or borehole collapse. Now, the build angle used as a noun refers to the inclination at a specific point in the wellbore. It is also known as the tangent angle, sail angle, or hold angle. Once the desired inclination is reached during the build-up phase, it is often maintained for a significant portion of the well. This steady section is called the hold or tangent section. Maintaining a consistent angle is important for precise directional control, reducing tortuosity, and ensuring that we stay within the planned well path. Closely related to the build-up rate is the turn rate. While BUR describes changes in inclination, up-down, the turn rate refers to changes in azimuth, or the compass direction of the wellbore. It's measured in degrees per 100 feet as well. For instance, if we're steering the well toward the east or south to hit a specific subsurface target, we're adjusting the azimuth, and that adjustment rate is the turn rate. Like build-up rate, this value is crucial in trajectory design and execution, ensuring we maintain smooth curvature and avoid overstressing drilling equipment. Course length is the measured depth difference between two stations in the well. Think of it as the distance along the hole between two survey points. It accounts for the actual drilled path, not the straight line distance. This term is used frequently in survey data and is critical in calculating the true vertical depth (TVD), inclination, and azimuth between points. Moving to spatial displacement, latitude in this context refers to the horizontal displacement in the north-south direction between two stations. It's part of the overall 3D coordinate calculation for a wellbore path. As we navigate through the subsurface, we need to monitor how far we've moved laterally, both north-south and east-west from the surface or a reference point. Complementary to latitude is departure, which refers to the east-west horizontal displacement of the wellbore. Both latitude and departure values are calculated from directional survey data, and together they help construct the plan view of the well path. This is particularly important in pad drilling or multi-well platforms where spacing and collision avoidance are key considerations. Finally, we come to closure, also known as target closure. This is the straight line horizontal distance from the surface location, or any point of interest, to the downhole target. It's important to note that this is not the measured path along the wellbore, but the direct horizontal offset. Continuing with these terminologies, kick-off point, often abbreviated as KOP. This is a very significant location in directional drilling. It's the precise depth in the vertical well bore where the deviation or inclination is first deliberately introduced. Essentially, it's the point where we start steering away from vertical to begin building angle toward the target. Selecting the right KOP is critical. Engineers consider factors like formation type, casing points, and target depth. Choosing it too shallow can cause instability, while choosing it too deep might make it hard to reach the target later. The process of initiating the deviation typically involves downhole motor assemblies with bent housings or rotary steerable systems, which gradually steer the bit in the desired direction. Next, we have the survey data sheet, which may also be referred to as a survey report or calculation sheet. It's a tabulated record containing all the measured survey data from downhole tools. These tools track inclination, azimuth, depth, and often gamma ray or resistivity data to help determine the well's trajectory. Survey sheets are essential during and after drilling. They help confirm that we're on course or alert us when corrective steering is required. Traditionally, these were printed sheets, but now they're digitized and integrated into real-time monitoring dashboards. Drilling engineers and directional drillers continuously update this data to calculate parameters like vertical section, horizontal displacement, and dogleg severity. The tangent refers to a portion of the well where both inclination and azimuth remain constant. This is often a planned straight section between the build and drop curves, particularly in S or J profile wells. Tangent sections are used to control trajectory and maintain a steady angle until the next course correction is required. From a mechanical perspective, tangent sections reduce wear and tear on the drill string and casing since the wellbore curvature is minimal. From a planning viewpoint, they allow for precise lateral positioning and help in placing the well within tight geological targets. True north is the direction that points directly toward the geographic North Pole. It differs from magnetic north, which is influenced by the Earth's magnetic field and can vary significantly depending on location. In directional drilling, this distinction matters. Survey tools measure azimuth using magnetic sensors, but we convert those readings to true north using a magnetic declination correction. Accurate directional surveys depend on this correction to ensure the wellbore is steered precisely toward the subsurface target. In offshore or Arctic operations, the difference between true and magnetic north can be dramatic, requiring careful calibration. TVD, or true vertical depth, is the actual vertical distance from the surface, or a reference datum, to a point in the wellbore. Unlike measured depth, which follows the well's trajectory, TVD is a straight-line vertical measurement. TVD is vital for reservoir mapping and pressure gradient calculations. For instance, formation pressure and pore pressure predictions are based on TVD, not measured depth. It also plays a role in mud weight design, casing depth selection, and determining the well's final landing point within the hydrocarbon-bearing formation. The last term on this slide is walk. This refers to the tendency of a directional well to drift laterally, especially in the horizontal plane, without deliberate steering input. Walk is often caused by the interaction between the drill bit and formation, tool face orientation, or rotational tendencies of the bottom hole assembly. In harder formations, the bit may naturally walk to one side due to unequal formation hardness, bit design, or side forces. Engineers analyze walk tendencies to predict and correct unintended deviations, especially in horizontal drilling, where staying within a narrow reservoir window is critical. Okay, so we have explained why surveys are required and gone through the major terms used in survey calculations. This covered a lot of terminology. This ends the first submodule of terminology and directional calculations. Please move on to the quiz before continuing. Thank you.